I'm Danielle Jacobs. I'm a professor of chemistry at Rider University. I'm chairing this morning's session. We're going to begin with Jeffrey Bode. In 1996, Jeffrey Bode received his BS and BA in chemistry and philosophy, respectively, from Trinity University in San Antonio, Texas, where he performed research synthesizing natural lignin lactones with Professor Michael Doyle. Greatly inspired by his undergraduate advisor to pursue organic chemistry, Jeff moved to Los Angeles to begin graduate studies at Caltech with Professor Eric Carrera, and after only 2 years, followed him to the Swiss Federal Institute of Technology in Zurich. Although I imagine the 24 hours of cramped airplane seating initially made him reconsider the move to Zurich, in 2001 he finished his doctoral studies, which focused on the stereoselective synthesis of polyketide macrolides, including apothalones A and B, via directed nitrile oxide cycloaddition. From 2001 to 2003, Dr. Bode pursued a diversity of small molecule methodology development as a JSPS postdoctoral fellow at the Tokyo Institute of Technology with Professor Keisuke Suzuki, and afterward joined the faculty at the University of California at Santa Barbara as an assistant professor of chemistry and biochemistry. In 2007, he moved to the University of Pennsylvania as an associate professor before ultimately returning to ETH Zurich as a full professor in 2010. Professor Bode currently holds joint appointments at both ETH and the Institute of Transformative Biomolecules in Nagoya, Japan. And by the way, Dr. Bode wants me to announce that you should not miss Wednesday's talk in the morning by Ken Itami, the director of the Institute of Transformative Biomolecules. Dr. Bode leads an impressively international research group that investigates new reaction methodologies towards the synthesis of small molecules, proteins, glycopeptides, and polymers that are currently out of reach by known reaction methodologies. What I found most intriguing about his research is what's listed on his group's webpage under the category of super secret, unconventional, and high-risk projects, a category which, while playfully ominous, truly complements Dr. Bode's appreciation of risk-taking creativity and inspiration towards creating new powerful tools for synthesis. Not surprising given the clearly unconventional route that he's taken to his career. Since the beginning of his academic career just 12 years ago, Dr. Bode has published 109 articles, 2 book chapters, and a handful of patents with his 70-plus graduate students and postdoctoral associates. The accolades and fellowships Dr. Bode has been awarded throughout his burgeoning career could take minutes to list, but most notably his 2008 ACS Cope Scholar Award, his 2010 Harada Memorial Lectureship and Gold Medal, and his 2011 ACS E.J. Corey Award, all underscore his outstanding contributions to the organic chemist synthetic tool belt. So please join me in welcoming Professor Jeffrey Bode as he delves into his laboratory's recent developments in cross-coupling methodology in his presentation concisely entitled Cross-Coupling 2.0.
Thank you, Danielle. That was probably the best introduction I've ever heard, at least for myself. So thank you very much for that. And also big thanks to Marissa for the invitation to come here. It's really an honor to speak at the National Organic Symposium. So I titled my talk Cross-Coupling 2.0. And I think this really reflects that we do chemistry in what we can call the cross-coupling era. Like it or not, this is the way we put molecules together, the way we think about developing new methodologies, and it is incredibly widely used. And for the purposes of our research, we define a cross-coupling as 2 molecules that have 2 specific functional groups. And under a defined set of conditions, those 2 functional groups will come together to form a new covalent bond. And I think we're all familiar with this, and we're all used to thinking about some of the disadvantages of cross-couplings. They're easy to criticize as having expensive starting materials, as having this pre-functionalization step where we have to do something ahead of time to put in those functional groups. And as we all know, there are often a lot of optimization that needs to be done to get any given cross-coupling reaction to work. But I think there's also a lot of advantages to cross-coupling. We have predictable, identifiable bond formations and very high chemoselectivity. And I think if we went back to the first or even the first few National Organic Symposiums, a transformation like this would look like absolute magic. That you could take a molecule like this and break it up into two relatively small pieces. This one's commercially available. This one you can make in 2 or 3 steps. And put together molecules like this simply and predictably is something that is transformative about cross-couplings. Nowadays, there are many commercially available building blocks. This is a cottage industry of companies that prepare these pre-functionalized building blocks, allowing people, particularly medicinal chemists, to buy them and very quickly assemble complicated molecules. And I think for all of these reasons, we now think about the world in this way. How do we identify these predictable disconnections? What functional groups do we need? Where do we get the building blocks? And then we can start putting these molecules together. So given that, we can ask the question, what is there to do now? What kind of research should we be doing? Well, one is we would like to have new cross-coupling reactions. What new types of bonds, what new types of molecules can we make using the same principles that are inherent to cross-coupling? We also have, I would argue, cross-coupling without pre-functionalization. This is this field of CH activation or CH functionalization, where we simply replace one of the functional groups with a hydrogen atom. And this creates some confusion sometimes about which hydrogen atom is your functional group in the transformation. But conceptually, I think it's an outstanding way to bring cross-coupling to substrates that we cannot readily access. Finally, I will argue that there's another class of cross-coupling reactions which we can term chemical ligation. This is just a cross-coupling reaction where there are no reagents and no catalyst. We pre-install 2 functional groups, and when we bring those molecules and those functional groups together, we form, without anything else in the reaction, a new bond. And I'll talk today about 2 areas in our group, one about new cross-coupling reactions, and the other about new chemoselective reactions. So what do we want to make? In the arena of small molecule cross-couplings, we saw beautiful talks yesterday about saturated N heterocycles. These are extremely important intermediates. I can skip a lot of the introduction about how prevalent they are in pharmaceutical compounds, how difficult they are to make, and just put up some structures that you would like to be able to make by a cross-coupling approach. And again, the trick is imagining a disconnection and then trying to figure out what these little dots or these little functional groups could be so that we could bring molecules together in one step. And then expanding that to ever sort of more complicated structures, such as these, or spirocyclic structures, or bicyclic structures. And now, just as a sort of spoiler alert, we're now able to do almost everything that's on this slide, one-step approaches to these kind of cross-coupling problems. And the other cross-coupling or ligation approach that is very important right now, particularly in the pharmaceutical industry, is the coupling of large molecules. So antibody-drug conjugates is transforming the way that we treat cancer, but it's really just the tip of the iceberg. So emerging ideas in cancer immunotherapy, targeted treatments rely on the ability to take 2 large molecules, an antibody, molecular weight in the hundreds of thousands, and another molecule, and bring them together in a selective fashion. So this is a huge synthetic problem. But it doesn't stop here. We're interested in protein-protein conjugates, 2 proteins that are covalently linked. This is extremely important in the field of ubiquitinated proteins and sumoylated proteins, which may be as important to human biology and medicine as phosphorylation and kinase inhibitors. Right now, we're incredibly limited in developing assays because we don't have access to these kind of homogeneous protein-protein conjugates. And also, we're interested in protein dimers, oligomers. This gets into targeted therapy, but also just in making molecules, therapeutics that are easier to administer, that have longer lifetimes, better safety profiles, requires that we be able to put very large molecules together. So we reduce this to this problem. So here are 2 large molecules, 2 proteins, for example, and we need to find functional groups that we can install in these molecules, mix them together, and form a new covalent bond. So in the first part of my talk, I'll talk about this idea of how do we look at a molecule like this and try to identify a way that we can develop a cross-coupling approach that allows us to take 2 simple, stable, ideally commercially available molecules and bring them together in one step to form structures like this. And this started in our group about 4 years ago when we became interested in this problem of synthesizing saturated and heterocycles. And I always tell my students, my graduate students, you need to have a dream, okay? Not graduating from graduate school or finding a girlfriend or something like that. You need to have a dream for your chemistry. You need to figure out what you want to make. What product do you want to have? And then imagine what is the best possible reaction that you can have. You'll probably be disappointed. You'll probably not be able to have that perfect reaction. But you should at least know what the goal will be. And so for this concept of making saturated and heterocycles by our dream reaction, we said, okay, we want a functional group here, a functional group here. We really wanted to have an unprotected nitrogen here. We had suffered with some methodologies where we could never remove the nitrogen protecting group. And so we put those criteria as sort of priority in developing methods. And at the time, the closest thing to this dream was a Negishi-type cross-coupling reaction, where you could take a Bach piperidine, you could lithiate it, you could transmetallate it to zinc, and then you could cross-couple it with palladium to a variety of aromatic halides. So this is good, but this is tedious. My students, they don't like to come in so early in the morning, get the dry ice, and this takes, 6 hours to lithiate. They have to warm it up, cool it down, and so on. But we did use this, and this is actually this is really outstanding chemistry. But it didn't work for the substrates we really needed at the time, which was morpholines and thiomorpholines. As soon as you lithiate this opens up, and you do not get your cross-coupled product. And we're, of course, not the only group thinking about this. There's lots of activity, especially nowadays, in this area. And there's been elegant work in cross-coupling approaches using CH activation, also radical-based approaches such as this. And then the very nice work we heard yesterday from Dave McMillan on radical-based approaches. And then what I really like, the work from Dave and Abby Doyle, where we do have something very close to the dream, this photocatalytic cross-coupling of an aryl bromide and this carboxylic acid that serves as the functional group for this kind of cross-coupling. So the situation is now getting better, and it's exciting to see these kind of new developments. We eventually gave up on this disconnection. So we thought, instead of breaking here, and reducing it to these kind of starting materials, we actually took the approach of let's break this carbon-carbon bond. And we like that because this would reduce to an imine, and the imine would give us an aldehyde as one of our starting materials. And then we just needed to figure out what kind of functional group 2 we could have to do this. And aldehydes are great. These are some of the most widely available starting materials and often very easy to install into your substrates. So we looked at the ideas we can get from cross-coupling, so halides. This didn't work because this just cyclizes, and then magnesium, zinc, boronic acid. All of these have some problems in terms of reagent stability. But that left us with these other cross-coupling partners like stananes, silanes, and carboxylic acids. And we chose stananes because I had a really fantastic student, Vaughn, who was working on this project. She worked for well over a year without a single result, trying different kinds of approaches. And she was the one who found this somewhat obscure but somewhat promising reference in which this organostanane adds to an imine in the presence of copper or silver triflate. And so she prepared this kind of reagent, she could form this imine and then started examining conditions for this cyclization. And although the reported conditions didn't work in this case, we could find, I'd like to say quickly, but it wasn't, we could eventually find two important things for this reaction. You need hexafluoroisopropanol as a solvent, or at least as a co-solvent. And it's also very helpful to have some kind of ligand for copper. And in her case, 2,6-lutidine proved to be optimal. So with those two changes, we had a very nice cyclization at room temperature that formed from the aldehyde and this reagent, this unprotected thiomorpholine in good yield. Just very quickly, we found that this had good substrate scope. Your standard array of aromatics, electron-rich, electron-deficient, were fine. This is a very easy reaction to run. You mix these together to form the imine. You mix the copper and the lutidine, and you combine this together and just leave it overnight. It's not sensitive to air or anything like that. And you do an aqueous workup. We do have tin in there, and I'll come back to that. But our products are the unprotected heterocycles. So we have a basic amine, and we have a very polar tin impurity. So we do an aqueous extraction, and we push this through a little plug of silica gel, and basically all of the tin is gone. Don't be scared of that. It's really quite simple to remove in this particular chemistry. What was also very nice is we found a higher than expected functional group tolerance. So we could have aromatic N heterocycles, we could have aliphatics, we could have glyoxaldehydes, all of which worked reasonably well. There was only one substrate that did not work, and that was this 2-substituted pyridine. And I'll come back to that in a little bit. So let me be the first to say that this is not going to win the presidential award in green chemistry. Okay? This reaction does everything that you are not supposed to do in 2012 or whenever we invented it. It has tin. It's stoichiometric in copper. It uses chlorinated and fluorinated solvents. It's not enantioselective. Okay? It does need to be somewhat dry so we don't hydrolyze the imine. But on the other hand, this has fantastic substrate scope, and you will see even more. The starting materials are readily available, aldehydes, and I'll tell you about the SNAP reagents. And we get, importantly, directly the unprotected nitrogen products. You can take these and you can use them immediately. And I'd like to contrast this to some other work from our group in N-heterocyclic carbene catalyst, which is perfect in the sense that it's catalytic. There are no byproducts. It's 100% atom economical. It works in nice solvents. It's always 99.9 something% enantiomeric excess. But it has two major problems. Okay, one is that the utility is relatively low. You know, this looks like a fancy molecule, but actually nobody really wants this kind of molecule. And even if you did, there's nobody who can look at this molecule and reduce it to these two starting materials. You can say, I'm going to make this in one step. So maybe Larry Overman can do this. You know, I remember as a young undergraduate spending entirely three days trying to figure out what an aza-Kopmanek reaction is. And it's such a powerful transformation, but it's not one that you can see. And I think if we really want people to use our chemistry nowadays, we have to make it visible, make it understandable. And I think in our case, beautiful chemistry, beautiful mechanisms, but very, very hard to use from the outside world. Okay, so how about the reagents? Well, we now have a whole line of what we call SNAP reagents. And so this works for many different ring sizes, many different substrate classes. We were fortunate to have a little bit of funding from the European Research Council with the aim of getting these commercialized. And we had this very bizarre series of conversations with chemical companies like Aldrich and others, where we called them and we told them we wanted to pay them to commercialize something. So in the end, we actually had a very outstanding arrangement with Aldrich where we provided a little bit of the funding. They made much more of the reagent than we could ever have possibly afforded on our own. And these are coming to market right now. There's 12 of them will be available. I think there are 6 or 7 that are available as of today. And because we were able to provide some of the initial funding, Aldrich agreed to bring them to market at a very reasonable price. So 50 Swiss francs per gram, and you can buy all of these plus another 5 that I'll show you in a little bit. So you'll be able to take any of these reagents, your favorite aldehyde, and a single set of conditions. For all reagents, all aldehydes, we have one set of conditions and form directly these kind of heterocycles. And very quickly, I'll show you just a few things about the scope. So we can make piperazines, and again, aliphatics, heteroaromatics, things like that. Same thing for the morpholines. We can make larger rings, so we can make 7-membered rings, diazepanes, benzodiazepanes. We can make oxazepanes, thioxazepanes, etc. My students got a little crazy here, and they went on to make like 8 and 9 and 10-membered rings, which actually work. The yields do go down when you start getting to larger rings, but even with unconstrained systems, we can still get 30, 40% yields for larger systems. You can make substituted SNAP reagents, so some of these are actually available. So you can introduce a substituent onto the SNAP reagent yourself, and then take your aldehyde and diastereoselectively form these di-substituted morpholines and piperazines. You can take ketones as substrates. Not every ketone works, but the important ones do. So now you can take, commercially available SNAP reagent, commercially available ketone, and in one step you can form these kind of systems. And I think it's absolutely incredible that very soon when these reagents come on the market, you'll be able to take these things and make these kind of molecules in basically one step. So, and what we're doing now is we're developing sort of custom or bespoke SNAP reagents. A lot of these are geared towards the linker groups that are common in pharmaceutical development to saturated bicyclic systems or spirocyclic systems. So we have these more specialized SNAP reagents that you can take and convert into these kind of products. 5 of them are commercially available or will be commercially available. Here's 4 of them here. And there's a lot of information on this slide. I just want you to appreciate that all of these molecules are now one-step syntheses from commercial materials. And it tolerates the kind of things you'd like to have. So boronic acids, aldehydes, esters, nitriles, things that you can take and then immediately use in a next step. So this is where we are. We have these reagents, great substrate scope, standard conditions, but of course there's still some problems. So, we know the tin is not desirable. I've actually been very surprised. Most medicinal chemists are not particularly bothered by this. If there's no other way to make these molecules, they've been perfectly happy to use the tin reagents. But of course, we'd like to find something else. Right now, we're somewhat limited. We always need a heteroatom here, so we're working on this. But the biggest problems we thought is, it's stoichiometric in copper, it's always racemic, and then most concerningly, we have this class, very important class of substrates that do not work. And we thought we could perhaps address these by developing new ligands for the SNAP chemistry. And to do this, we need to know something about the mechanism. So when we first got into this, we really thought this is like a Lewis acid 2-electron process. I think maybe this is just the way that we're used to thinking about chemistry. And this is also what was written in Kagoshima's report. And we were therefore very surprised that this substrate did not work. If this is Lewis acid chemistry, this should be an even better substrate. And we did a series of experiments, and I'm just going to show one here, where we sort of slowly realized that this is probably in fact some kind of radical-based reaction. And our current hypothesis is that the copper-2 oxidizes this carbon-tin bond to generate this stabilized radical. And this undergoes a 6-endo cyclization to form the more stable nitrogen-centered radical. And the copper-1 that's formed here actually then reduces this radical to bring us back to copper 2 and the product. And the reason we thought that it's not catalytic is now the product is such a good ligand for copper 2 that we just have product inhibition. And so if that's the case, you should, or you might be able to find a ligand for copper that will outcompete the product. And so although a lot of the sort of very good ligands for copper either didn't work or were not catalytic, we did eventually find that these Box ligands are very good ligands. So this phenyl Box ligand will allow us to do this in basically very good yield. Before you ask, yes, it's enantioselective. selective. No, it's not at a really useful level yet, but at least in principle, you can form these products in about 40 to 50% enantiomeric excess. So if anyone has great Box ligands, please try this. But most importantly, these catalytic conditions expand the substrate scope. By putting a good ligand on copper, we're able to bring in these aldehydes that did not work before. So we can have a whole range of these alpha-substituted piperidines and other substrates that did not necessarily work under our stoichiometric conditions. So that's good. Okay, and so what about the tin, right? What could you do to get away from the tin? Well, we've already excluded these, and we're left with silanes and carboxylic acids. And I was really convinced this would work. If you take the silane, this doesn't work under our conditions. We spent a long time trying decarboxylations, making silver salts, even making Barton esters, and none of those worked either. But as we learned from Macmillan yesterday, these photocatalytic reactions, this is transforming the way we do and think about chemistry. And this provides an opportunity for us as well. So this report from Nishibayashi described the formation of presumably a radical from this organosilane and conjugate addition to form this product here. And so we can make that kind of SNAP reagent with the N-phenyl group here. And that works very nicely. So you can, in fact, do this under these photocatalytic conditions. The only problem is I would not let my student publish this result, because we have this N-phenyl group here, which you'll never get rid of. And I said, that's great, congratulations, but no, go make it work with Bach. So you take the Bach one, and you try this, and of course, you don't get any reaction. You really need this stabilized radical. Well, my student, Shenying, he is persistent both in chemistry and also in arguing with me. So he came back and said, well, I can't do the Bach, but I can do the benzyl. And it's almost as good. So I said, fine. Okay, we'll live with the benzyl group. And so that works quite nicely. Very simple reaction conditions. We form the imine. We shine light with 1 mole% of this catalyst. Very fast reaction. Usually it's done within 2 hours. And again, we see the same, very good, slightly different than the SNAP chemistry, but still quite good substrate scope. Still a lot of things to be done. These conditions don't work for all of the different classes of reagents, but I think at least there's hope. And so now, we have these commercially available reagents where we can take, in one step, we can form these heterocycles in small amounts. And I think this is great for libraries and for lead optimization. And I think at least we have hope that if we do need to scale this up and get away from the tin, we can use some of these more modern methodologies to do that. Okay, so our next problem. And this is, I have to say, really been a big part of our group for the last 12 years, is thinking about this question of how do you take large, unprotected molecules and put them together. So this is, again, we classified this as a very special case of cross-coupling. We have these big molecules, lots of unprotected groups. We need to find 2 special orthogonal functional groups that are only going to react with each other. And it would be really helpful if this is compatible with water and we don't have to add any reagents or so to do this. And we've been interested in many types of covalent bonds, but I'm going to focus on amides for this talk. And the reason, or one of the reasons you want to do this is for peptide and protein synthesis. So solid phase peptide synthesis, this is a phenomenal achievement in organic chemistry. It takes a little while to learn the intricacies, but it's very easy to get started. You can buy all the reagents. The catalogs tell you what to do. And so you can get going very quickly. And you can use this to make fragments or segments up to about 40 amino acids. We do an enormous amount of peptide chemistry in my group now, and I can tell you that you can go up to about 40. You cannot go much beyond that. There's a number of reasons for that, but that's really the limit. It's still fantastic, though. But you can get up to about 40. You can get these segments very pure, and you can do this on hundreds of gram scale even, but hundreds of milligrams is what we normally do in our lab. And now the trick is just to find these functional groups that you can mix these fragments together and get an amide bond. So we're not the first person to think about this. Is actually the peptide chemists have been thinking about this problem for years, and fantastic work from Kemp and so many people, Tam, and especially Stephen Kent, who popularized the native chemical ligation. And he uses a thioester here and a cysteine. And this allows you to do exactly what you want. You combine these together, you get this intermediate, and this rearranges to give you this amide bond. Works on completely unprotected peptides, and this has revolutionized the field of chemical protein synthesis. There are some limitations to this chemistry and reasons to want other reactions like this. And so our group has developed an alternative that we call the CAHA ligation, ketoacid hydroxylamine amide ligation. It uses two somewhat common but still very unique functional groups, an alpha ketoacid and a hydroxylamine. And if you just mix these together in a polar solvent or water, you get amide bond formation and carbon dioxide as a byproduct. So you don't need any coupling reagents, and as you'll see, this is a very chemoselective process. It takes advantage of the fact that a ketoacid is really its own unique functional group. It is neither ketone nor carboxylic acid. And the same thing is true of the hydroxylamine. They really have their own personality. And you can kind of think of this as like teenagers in love. You put these two things together and they just ignore the rest of the world and come together and couple. So, if we want to take advantage of this, we have to have a way of making them. We need to interface with this very well-established FMOX solid phase peptide synthesis so that we can provide reagents and resins that are completely transparent to the existing chemistry. And I will be the first to admit I was totally naive about how difficult this was going to be. And you see lots of names down here. Many, many students and postdocs worked on this problem so that we can have new chemistries, new linkers that do exactly that. And so I'm going to unfortunately skip their years of development and just show you the reagents we have now. We have a couple classes of linkers, so we have this on tens of gram scale. We have these cyclic hydroxylamines that we like to use for the ligation. We have these on gram scale. These are currently being commercialized. You should be able to buy them by the end of the year. So we have these, and we take it and we do peptide synthesis on automated solid phase peptide synthesizers. We purify that by reverse phase HPLC. You make the segments and you're ready to go. And so once you have the segments, you can start putting together proteins. So this is an example that we did in a laboratory in Nagoya. We made 5 segments and we used 4 ligations to combine this together, fold this protein, and so we can make proteins up to about 200 residues. These are all targets that we have finished in our group. Many of them are either submitted or coming out, hopefully in the next few months. So this works. You can do this. Let me show you one example very quickly, just how the chemistry works. So we make our segments. So here's the hydroxylamine, here's the ketoacid. In this case, we use this 5-membered ring that gives us a non-canonical residue in oxyproline, a homoserine. But we found that for most of our chemical biology work, this is perfectly fine. So you combine these together, that's your starting material, that's your ligation product. You can then do a next ligation, isolate this compound here, and now do a final ligation where we have one segment here, the ketoacid, and this hydroxylamine. Again, starting materials here, that's the ligated product. That's the purified one. This is 100 amino acids. This chemistry works very, very well. Once you have this, we can fold it. This is sumo. And we can take sumo, and then we can use an enzyme or a series of enzymes to conjugate sumo onto a target protein. And we do a lot of chemical biology with this. But okay, now I did all this work with synthetic chemistry, and then when we get to the really interesting step, putting one protein onto another, we have to use an enzyme. Okay? That's fine, and for this project, that's actually perfect. But you would like to be able to do that without the enzyme. You'd like to have completely chemical approaches to doing this. And that brings me to this problem, what I think is really both intellectually and practically one of the most difficult problems in synthetic organic chemistry, which is how do you take two large molecules, folded proteins, where you have a very strict set of criteria, and put them together. And I think this is a hard problem to appreciate because of this. We need, sorry, this is missing. We need to do this at 100 micromolar or less. And why is that? Well, chemistry changes with molecular weight. If we take a small molecule, like protected glycine, if we have 10 milligrams of that and dissolve it in 2.5 milliliters of solvent, we get a 20 millimolar solution, 0.02 molar. That is, for an organic chemist, very dilute. Right? Process chemists would be extremely unhappy if you bring them 0.02 molar. But if I have even a little tiny protein, if I have 10 milligrams of that, I would love to have 20 millimolar. I can only use 25 microliters of solvent. That's not going to happen. So if we have this and we dissolve it in 10 milligrams, we'll be pretty happy to get 200 micromolar. Remember, I want to ligate this to another protein, so I've got to put another 10 milligrams in there. So realistically, you have to do these ligations at 50 micromolar, 100 micromolar, 10 micromolar would be even better. This is a requirement. You will not get your protein soluble at 100 millimolar. You have to be in the micromolar. So what's the problem with that? Well, the problem is rate. So this is just math. If you take one equivalent of one protein and one equivalent of the other, and we look at the conversion as a function of the second order rate constant, you get a chart that looks like this. So what this tells you is that if you're going to do this reaction, you need to have a reaction that is at least 10 per molar per second. Okay? This is just math. It's not you can't just wait forever. If your rate constant is here, it's never going to get done. And the problem is, there's almost no organic chemistry, at least chemoselective organic chemistry, that's anywhere close to this rate. 1 per molar per second is already very fast for a chemoselective reaction. So our CAHA ligation is actually not bad, 0.01 per molar per second, but not good enough. NCl is better, but still not good enough. This is why people use click reaction. Click with stoichiometric copper is 2 per molar per second. That's one of the fastest couplings that's chemoselective that we know. And the other faster reactions, so thiolmaleimide, we've measured this in our lab at 700 per molar per second in most cases, depending on the pH, but very fast reaction. And every pegylated protein, every antibody drug conjugate that's ever come to market has been made with this reaction, and only this reaction, because it's the only thing that's fast enough. So how do we fix this? So these are the kind of problems that I like to give my students. Yeah, great, you made this big protein, that's nice. Go make the CAHA ligation faster. And by the way, no reagents, no catalysts, water, 23 degrees Celsius. So as long as you keep all that the same, you can do whatever you like. Right. So the only thing you can change is the starting materials. And so, we know that keto acid has an electrophilic carbonyl and something here, and we spent years on the hydroxylamine, so nobody wants to touch those. And so we started looking for better keto acids, and we tried lots of things. Acyl phosphonates, they work, but they're even slower. Acylsilanes do not work. And then from my former colleague, Gary Molander, we got this bizarre looking molecule, this acyl trifluoroborate. And this actually works. And these are actually incredibly stable molecules. Once you figure out how to make them, Once you have them, they are fantastic. They're far more stable than any kind of organoboron compound we've worked with. You can put them on water, you can boil them, you can leave them out in the air. They're really nice compounds to work with. And they do one thing very well, which is this ligation. So if you take hydroxylamine and this acyl trifluoroborate, now we perform this ligation under acidic conditions, we have over 20 per molar per second. This is a remarkably fast reaction. We had this result for a long time, and the only problem was we didn't know how to make these compounds. So Gary's group, they spent a long time trying to develop chemistry and had given us the first compounds. But in order to go forward, we really needed new methods to make them. And so you get a postdoc in the group and say, we got this great new chemistry, go make these compounds. And if they were a good postdoc, they'd come back with this book that basically says, these compounds are stable, prone to rearrangement, and are not going to be made. So I hate this book. This book set our chemistry back by 3 years. This is not true. These are perfectly fine once you know how to make them. And Gary had made them this way by lithiation, trapping, and then treatment with KHF2. And we came up eventually with several ways of doing it, but for many things we needed to avoid this KHF2. This is very abrasive conditions, and we needed a little bit milder conditions here as well. And so this is again how we do chemistry in our group. You ask the postdoc, this is what we want, this is what you get to start with, this is what you need to figure out. So just find some reagent that will do this. And so I had a very good postdoc, Gabor, who worked on this, and he thought I can convert this to the lithium and develop some type of new functional group, new acyl borane derivative that can give this in one step. And he eventually did this. I don't have time to go through everything, but we came up with these zwitterionic salts that are both very soluble, and this one's also crystalline. So you just mix your aryl halide and this reagent together, you add butyl lithium at -78, warm it up, and then we just need to add aqueous KHF2 and acetone to precipitate this. So this works for many things, heteroaromatics, and I don't have aliphatics and more exotic things on here as well, but we have conditions for that as well. So what can you do? Well, now we can finally do these ligations the way that we wanted. So we can make a very big peptide, and we can put, for example, on the side chain the hydroxylamine. And we can put a polymer, molecular weight 20,000 peg, for example, on an acyl trifluoroborate. And then using 1-to-1 stoichiometry, we can mix these together, and in basically a minute, the reaction is finished. These are reactions that we struggled with for many years. And we have things like where we're making polyvalent peptide conjugates where we could never get this chemistry to work, that now in 5 or 10 minutes we can make things that are huge molecular weight, 20,000 molecular weight, just in a matter of minutes. And I'll show you just one example. This is a big part of my group that we still struggle with. This chemistry is still not perfect, but it's finally good enough to do something that we've always wanted to do. And that's, it sounds simple, but take 2 proteins and a big polymer, basically close to stoichiometric amounts, and combine it together. So we can express GFP, we put in a mutation here. We still have to use this maleimide chemistry to bring in the hydroxylamine. Sorry, that's supposed to be a hydroxylamine. Then we can take these molecular weight, 20,000, 40,000 pegs, and we combine this together and we get the protein dimer. And you can see this by gel. Here's our starting material. Here's the monomer, and depending on how much we add, so if we add less than stoichiometric amount of polymer, we see some monomer. If we add stoichiometric amounts, we see mostly the dimeric product. This is some decomposed or unlabeled starting material here. So we're finally getting there. And now we can make tetramers, octamers. We can make heterodimeric systems where we combine polymer, protein A and protein B. And this opens up, I hope, a lot of areas for making very large constructs using synthetic chemistry and addressing some of the problems that are important now in the pharmaceutical industry. So with that, we'll conclude. So we really like this idea of cross-coupling, of thinking about the world in terms of functional groups. Finding 2 functional groups or functional group pairs that do very unique chemistry, either in the presence of a catalyst or just as a ligation on their own. And for all of this, I have to thank my students. You know, we all say this, but it's really true. I mean, we cannot do the kind of science without the students. And what I particularly love about my students is they're completely fearless. They're willing to go and do completely different things, you know, outside of what they're trained in, and certainly outside of what I know. So we have, you know, molecular biology in the group, cell biology, somebody's building a machine, other people are doing calculations, and this comes from them. And you know, what I want them to do is, if the next logical experiment is outside of our expertise, don't stop. You know, find someone to help you, come to me, tell me what you need. You know, we'll make this work. There's no line. We're scientists. We're not just chemists. So there's no line that we shouldn't cross. We should keep going until we get there. And for that, I really thank them. Thank you again for the invitation, and I'd be happy to answer any questions.
So one of the nice things about data chemical ligation is doing multiple times, multiple peptides together. If you looked at doing your coupling, or organizing your peptides into multiple peptides, 2, 3, 4, making larger fractions?
Yes, we certainly have done that. In fact, it's a lot easier in our case than native chemical ligation, because native chemical ligation, you need the cysteine residue. And so finding a cysteine residue every 30-something amino acids is quite difficult. So yeah, we've done up to 5 or 6 segments in preparing these proteins. And we also have the advantage that we can protect either the hydroxylamine or the keto acid. So we can carry those through, and we can often do in situ deprotection. NCL is better at what's called kinetically controlled ligations. So where you have 2 segments together, and then you add a third in later on. And we can do that to some extent, but not as well as NCL can right now.
Alex Grenning, University of Florida. My question stems from your mechanism of the snap reaction. Mm-hmm. So one of the implications of forming a N-centered radical cation is that if you had a carboxylate adjacent to it, you could do the decarboxylation and more cross-coupling. So have you thought about designing a snap reagent from serine?
We haven't done the unprotected one, but yes, we have done the snap reagents from serine or from cysteine, and you can get, the carboxylic acid exactly at that position there.
Will it decarboxylate, though, and then do cross-couplings?
Based on the results of Dave and Abby, I think it should. I don't think it'll do it in the same reaction, but we haven't tried. Yeah.
Jeff, in your ligation, are there some neighboring residue limitations? Because there have to be differences.
Yeah.
And where does that currently stand in terms of generality?
Yeah, so there are some neighboring, so let me get a good example. So on this position here, so for the keto acid, so we typically use leucine. We can use many. The reason we use leucine is that it's by far the most common residue. So it's 11% of human proteins have leucine. So we can use leucine, phenylalanine, tyrosine, arginine, alanine, glutamic acid. A few are not okay. Aspartic acid is not okay. I'm guessing that cysteine is not okay, but we've never tried. So there are some limitations, but I think we have, maybe half of the canonical amino acids that are suitable at that position. There are some neighboring effects, but they're actually relatively small. And then on this side, so unfortunately, you cannot just have a straight chain. So if you just have a O-methyl hydroxylamine where there's no strain in the ring, this is not sufficiently reactive enough with the keto acids. So we cannot do sort of every residue at this position here. So that's the main limitation that we have. Within that, if you work from the cyclic hydroxylamines, the ligations actually are remarkably good. It doesn't always go to completion, but it almost always works. And when it doesn't work, there's something wrong. And so we have a few cases where the protein has folded up so much inside itself that the ligation didn't work, and then we could put some backbone protection to wake it up, and then the ligation went.
Jeff, I have a question. With regards to your snap and slap, which I don't know what that means, With the SLAC reagents, is the hexafluoroisopropanol still required, and is there do you have any?
No, then it's
Yeah.
basically just like the photocatalytic reactions. So solvents like acetonitrile, methanol, things like that are good. So we're surprised how well it works. But yeah, you don't need the HFIP, and you don't, at least in this case with the piperidines, you don't need the copper either.
And so are you expecting that methodology will eventually replace the tin?
I don't think it will replace the tin for everything. I don't think we'll be able to generate as many radicals using that, but who knows? I mean, with some of the new co-catalysts and things like that, maybe we can oxidize stronger bonds. The one advantage of the tin, so if you're making a library, we have one condition that almost always works. And with the photocatalysis, I think you're not going to have as much generality as we have. So it's a bit of a trade-off between the two. So if you're just making a big library, I would stick with the tin. If you need to scale up or you know exactly what you want, then I would probably invest in the silicon-based reagents.
Sorry.
So the proteins that you've made, have you come across any that don't fold properly or fold differently than the natural protein?
Yeah, that's a very good question. So protein folding, I have to say, what we can do, and even what NCL can do, is we can pretty much make like single domain proteins, which, in our experience, almost always fold. We have some membrane integrated proteins that we've made now where, you can't fold them in the absence of a membrane. So those we have not, we don't know if we folded them or not, but I suspect not. But it's actually very hard to tell without a functional assay. I think the problem is, so protein folding, once you, if you have a single domain protein, you can usually fold it. And most proteins that are expressed from E. coli are very often refolded, so we can many times find good folding conditions. The problem starts is when you have a multi-domain protein, then those become very difficult to fold. And that's one of the reasons we need this better ligation, where you could make one protein domain, fold it, make the other protein domain, fold it, and then bring the folded domains together. And remember, protein folding like we have one protein that we fold over a week, so we just leave it in dialysis buffer in the cold room for a week. That's perfectly fine. But you cannot express that protein in E. coli because it folds so slowly that it just gets truncated. So you can get away with a lot more aggressive folding techniques with a synthetic protein than with an expressed protein. So.
No more questions? Then let's thank Dr. Bode one more time.